Alright, so today's set of notes we're going to start. So on the last set, we found for multivariable functions, again, two variable functions in this class, where critical values are. Alright, we take first derivative, set it equal to 0, and solve. And so the next step, just like with the one variable cases, well, now that we found critical values, they're the possible extrema, right? Possible maxes and mins. And so two variable functions, the critical values are where we get our extrema. In order to determine what they are, we actually have a test that we use. Right, it's very, very similar to the second derivative test that was used for one variable case. The only difference here is it's slightly more complicated because we've got multivariables. And so what we're going to be using what's called the second partials test. So we'll be using the second derivatives. It's also known as the D-test because a D formula is going to be created as an easy way to test if my critical values are extrema or not. Alright, so we'll test whether we have a max, min, or neither, which is called a saddle point, and I'll explain why the neither case is a saddle point once we get to that point in the notes. Alright, so find the critical values. In order to determine relative extrema, find the critical values. You find the first order derivatives. Again, there's three wet methods. You either use the algebra methods, substitution, or matrices, or the third method if they only have x values and y values individually you solve, right? Which was what we did in the last set of notes. Alright, so I went ahead and set one up for you. So I've got this function here, f of xy. I already found that it has critical values at negative 2, 4, 0, 0, and 525. Right? Again, I would have had to use the substitution rule because of this cube term. Alright, since we're testing to see if those critical values, I have three of them, so I'm going to test all three of them to see if they are max, mins, or neither cases. Well, it's the second partial derivative test, so I need my second derivative. Alright, now, we only find one mixed derivative, because remember, they're the same. You can find any one you want. We just, again, like to have everything kind of standard way to do things. And so we tell you to find the xy one, the xy mixed derivative. I have to find the xx, and I have to find the yy. But I only need one mixed derivative, because all of our examples have the same mixed derivative. Alright. Before I can get to my second derivatives, though, I need to get my first derivatives. Alright, so my first order derivative with respect to x. Alright, those are my x terms, so I get 12x to the second plus 40x minus 4x times y. Alright, now with respect to y, there's just two y terms. Alright, so my derivative with respect to y is 2y minus 2x squared. Alright, now I find my second. And again, we're going to find the second derivative with respect to each variable, f sub xx, f sub yy, and then one mixed derivative. You can find either one. We just, again, standardize it into finding it that one. But again, technically, you could find the yy. It's the exact same expression. Alright, so my first derivative with respect to x is where I'm looking. I'm going to take its derivative with respect to each variable. Alright, so the derivative of this with respect to x twice is 24x plus 40 minus 4y. And then the derivative with respect to y, that's the only y term. And so negative 4x. Alright, so done with those. There's my partial derivatives using my x first derivative. Now my second derivative with respect to y twice. So that one's easy. That one's just 2. Alright, so there's the three derivatives that I need. And now to the formula, what's called the D formula. That's why this is also known as the D formula test. Alright, so remember, we have critical values. So A, B is just a critical value. A is a number, B is a number that we found was a critical value. And so what we do is we throw them in this formula that organizes our second derivatives in a way that when I put my critical value in it, it tells me if I got possible max or min, or it's the neither case. And so the D formula is this. This is the general D formula. Alright, so AB would represent my critical value I'm plugging into it. And so I'm going to do the example for the one above. And so what it is, it's the second derivative function with respect to x times the second derivative function with respect to y minus the mixed derivative, second derivative, squared. Right? You know, that's really easy to forget that squared. And so for our function, I'm going to find that. So if I go find my second derivative with respect to x, well, that was the 24x plus 40 minus 4y, so that goes here. 24x plus 40 minus 4y times the second derivative with respect to y. My second derivative with respect to y was 2, so that's just times 2. Minus my mixed derivative squared. My mixed derivative was negative 4x. And don't forget, square the whole thing. So negative 4x, the whole, in parentheses, that whole thing gets squared, and this negative is outside that square. Alright, so I'm going to simplify. I'm going to distribute my 2, and I'm going to square my negative 4x. So when this function simplifies, this d-test for my f function, it simplifies to 48x plus 80 minus 8y minus 16, right? Negative 4 squared is 16, and x squared is x squared. All right, and I'm going to hold on to this. This is just the d formula for this particular function. All right, that d formula was found by taking the second derivative with respect to x times the second derivative with respect to y minus the second derivative with the mixed second derivative. Alright, that's how this formula was found. Alright, so this is the formula we use, the d-test formula. Alright, I'm going to come back to this. We will use this in when we go do and we'll test our critical values, but we're going to do that after we talk about how do we test them. Alright, so this is in general how we do it for any d formula. Alright, so the test there's 2 parts to this test. Alright, the first part is you plug your critical value into that d formula. Alright, you take your critical value AB, you plug it into the d-test formula, and you get one of 2 results. Either the value comes out positive and then there's more work to do, or the value comes out negative. Alright, and then I'll talk about that. Again, there's not as much work to do in that case. Alright, so that's the first step. The first thing you do is plug it into this d formula and see if it comes out positive or negative, and then you do 2 different things depending on which case it is. So if you plug it in and your d-test comes out positive, so when you plug that in, the d value is positive. Alright, when I plug it into my d-test. Now in this case, what that tells me is that my turning point, or my critical value, is a turning point. It's going to give me a max or min, which means that concavity is turning the same way in both directions, meaning they're either both concave up or both concave down. Alright, but I don't know which case it is. All the d-test tells me is that it's a possibility that it's either a maximum or a minimum. I don't know which case it is until I do one more step. Alright, so the one more step, so this is just the check. My d came out positive, and so that means that, excuse me, I do have an extrema, and now I figure out, well, which one do I have? Alright, well, you check concavity just like we did in the one variable case. Alright, so I take my second derivative with respect to x, just that, second derivative with respect to x. So I take f sub xx, plug in my critical value. If it comes out negative, well, that means, got a little weird on my concave down. And the d-test means it's concave down in both directions. And so that means it's concave down in the x direction, it's concave down in the y direction. And so in 3 dimensions, this would be the shape that we have out. And so that would give me out a relative maximum at f of AB. Alright, now, just so for your information, now we keep it standard, just like we could pick any of the mixed derivatives, we just standardize it as xx. Technically speaking, my f sub yy should come out, that's what the d-test is telling me, should come out the same. So if my xx came out negative at that point, my yy should also come out negative, and it tells you the same thing. It's concave down in the x direction, concave down in the y direction, which means it's totally concave down, and I've got a maximum. Alright, so that's if I plug it into my second derivative with respect to x twice, or respect to y tries, I've got a maximum. And then in the other case is, well, if it's concave up, right? I plug it into my second derivative with respect to, again, I'm plugging my critical value in, and it comes out positive. Right? That tells me it's concave up, right, if it comes out positive. Which means it's got this shape, and since it's positive in both directions, oops, yeah, that's right, concave up, this is the shape that's coming out. So I've got a relative minimum of whatever that function value is. Same thing would be true, again, we standardize it as xx, but if I plug it in my yy, it should also come out positive. Alright, because again, the d-test was saying they were moving in the same concavity direction. Both of them concave up in this case, and therefore, since they're both concave up in both directions, the whole thing's concave up, ergo minimum. Alright, so that's if the d-test comes out positive. I plugged it in my d formula. It came out positive, then I check concavity. Alright, concave up, concave down. The other possibility is if I plug it into that d formula, and so when I plug it into the d formula, my value that comes out is a negative value. Well, that tells me that my critical point is just a critical point, so it's not an extrema. We call these saddle points. Alright, the reason why is the shape, and I'm going to kind of explain why here, and then I'm going to go to the book just to show you a better looking picture than what I can draw. Alright, but what's happening is in one direction you have concave up. So suppose in the x direction it's concave up, but in the y direction it's concave down. Alright, but they do have a stopping point. Alright, that would be my critical value. But it's neither a max or min because, again, it's going down and up on either side of it. So compare it to when we had the single variable case. Remember, that was my critical value, but it was neither a max or min, right? It was a stopping point, but not a min. Same idea is happening here. For these saddle points, I've got a critical value, it's a stopping point, right? But it is neither a max or a min. And I'm going to go show you the picture on the for the saddle point in the book, just because it's just a little nicer picture, so you can kind of see what's going on. All right, so this is why we call it a saddle point. All right, because the shape that comes out on my three-dimensional graph is a saddle-like shape. And so here's, again, it's describing what's happening. So in this one that they've graphed here, is they've graphed that in the x direction it was concave up, in the y direction it was concave down, so they were doing different things in terms of concavity. They did have a stopping point, but it is neither a max nor a min. It's not a peak or a valley. So we call it a saddle point in those cases because that tells me, that describes the picture. All right, so when we have those, that's what we'll be using. We're using that term, saddle point. All right, now we're going to do the example from above, and this is where we'll stop today. All right, so using our example that I set up, so this was our function, these were our critical values that I found, so I'm going to write down the d-test that I found in the earlier portion of the notes. The d-test for this function, remember, was 48x plus 80 minus 8y minus 16x squared. All right, now I'm going to test each one of my points. So I'm going to test the first point, negative 2, 4. So I'm going to take my negative 2, 4, plug it into my d formula. It's not a negative 4, positive 4. All right, make sure you're just careful that negative 2 is being squared when you plug it in. All right, so when we plug in negative 2, negative 4, it comes out a negative number. All right, so my d-test came out negative, so that's the second case. That means negative 2, 4 is a critical, but a saddle point, meaning it's neither a max or a min. The shape of the graph is a saddle. You can read that, saddle point. Meaning it's not an extrema. Alright, it is neither a max nor a min. Alright, 0, 0. So now we're going to test 0, 0. Right, so again, first thing I do is plug 0, 0 into my formula. Alright, so 0, 0 is kind of nice. 48x will zero out, negative 8y will zero out, so I'm left with 80. Well, 80 is positive. Alright, so all that d-test there means that, yes, it's an extrema. I don't know which one. It's either a max or a min. All I know is, yep, they're both turning the same way. Both concave up or both concave down. I have to check to see which one it is. Alright, so again, we usually use f of xx, and I will. So if you remember, our f of xx formula was 24x plus 40 minus 4y. We plug in our 0, 0, which comes out 40. Well, 40 was positive, and so that means concave up. And so since it's an extrema and the shape is concave up, at 0, 0, we find a relative minimum. Right, so if I plug 0, 0 into my function, it would give me a relative minimum. Alright, just a note on this. If you had checked YY, that was the easier case in this one. Remember, YY was just 2. It tells you the same thing. Alright, concave up. And that will always be true because that's basically what the D formula is telling you. The D formula is telling you you have the same concavity in both directions. Alright, so if one of them comes out concave up, so should the other one based on the fact the D-test was positive. Alright, now the last one. Alright, so test the last point, which was 525. So first thing we do is we plug it into the D formula, which was 48 times 5 plus 80 minus 8 times the 25 minus 16 times 5 squared. Alright, when we plug those in, it comes out negative. Alright, so then we're done. It's kind of, when it comes out negative, right, D formula came out negative 280, that I'm done there. So that means the point 525 is a critical, but it's a saddle point. I'm just going to say it's a saddle point. Alright, it's a stopping point, but it is neither a max nor min. It's that saddle shape, which is why we call it a saddle point, because it's descriptive of what the shape is. Alright, so that finishes up there. The next set of notes will be then practicing that. Alright, so we'll be finding critical values, determining if they're maxes or mins. So kind of putting it all together in the next part. Alright, so I'm going to stop this set of notes there.